Hi, welcome to this particular module, and in this module what we will look at, we will look at the another modality except mechanical to find out whether the tissue is cancerous or not. And as we have discussed earlier, we are right now focusing on breast cancer. So, when you talk about breast cancer, we have seen that as the disease progresses, the morphology also changes, right. And we have seen in the last lecture how we can understand the stiffness of the tissue, or how we can measure the stiffness of the tissue using piezoresistive microcantilever, right. So, in this class let us see that except stiffness, what are other characteristics. Can we measure the electrical property of tissue, or can we do both things together, that is electrical plus mechanical property. When I say mechanical property, it is nothing but the elasticity or the stiffness of the tissue, right. So, if you quickly see what we have discussed in last class, you will see on the slide, and that will be our piezoresistive microcantilever. We have seen the process flow of how we can design this particular microcantilever, and then we have seen how we can use this microcantilever, and we have also seen the results, right. When we measure the epithelial region, tissues from epithelial region, tissues from stromal region, also the tissues from benign region and cancerous region, right. And we can clearly see that we with the help of piezoresistive microcantilever, we are able to delineate whether the tissue is normal or benign or it is cancer, correct. Now, in this particular module, let us see quickly what is the structure of breast or breast anatomy. Now, if you see on this particular figure, what we see is that breast consists of lobes, ducts, fat and pectoral muscles. We also discussed this earlier, right. It is just to revise. And if the cancer occurs in duct, it is a ductal cancer. If it occurs in lobes, lobular cancer, right. If it is mixed, it is mixed tumor cancer. If it is inflammatory, inflammatory cancer. If it is mucinous, mucinous cancer, right. And then we have seen that the cancer can be two types, one is invasive, one is non-invasive. So, on the right side, let us see, on the right side we see that if the tissues, when the tissues are taken from the stromal region and from the epithelial region, and if the tissue is normal, this two on the left is normal, on the right this is cancer, alright. So, I am just saying this particular tissues are cancer, these are normal. So, these are SEM image of the tissues, SEM image of breast tissues, and these breast tissues are nothing but tissues that are taken out with the help of biopsy, with the help of biopsy, BIOPSY. Alright. So, when you see the SEM image of the tissue normal versus cancer, we can clearly see that there is some kind of roughness in the cancerous tissues, while the normal tissues or the benign tissues, right, they are comparatively smoother, right, compared to the cancerous tissues. So, what does that mean? That means that if the morphology of the tissue is different, if the morphology of this tissue, that is normal tissues, is different than the cancerous tissue, then we can probably understand its electrical property, and it should be different, while if the electrical property is different, its thermal property can also be different. That means that apart from stiffness of the tissue, we can measure the resistance of the tissue, or we can measure the thermal conductivity of tissue, correct. We can measure the resistivity, resistance, or we can say impedance, right. I will just write down impedance symbol Z. Stiffness, this is mechanical property, impedance or resistance is electrical property, and the thermal conductivity is thermal property. So, EMT, electrical, mechanical and thermal property of tissue. Alright guys. So, now before we understand how we can design a sensor that can measure this electrical and mechanical property of the tissue, let us quickly see what is the breast anatomy, and also let us understand what is breast cancer and what are the stages of breast cancer. Alright. So, the video here, right, that is about the breast anatomy, while the second video will show you what exactly breast cancer means and what are the stages of breast cancer. So, as we can see from the video, right, breast cancer have different stages, and it at certain point we can understand whether it is invasive or non-invasive type of cancer, right. Now, for a given tissue from the biopsy, can we measure the electrical and mechanical property of tissue? That is why we say electromechanical phenotyping of breast cancer using flexible microelectromechanical sensors, So, what should be the role of this sensor? This sensor should be able to delineate cancer and normal with the help of electrical sensing and with the help of mechanical sensing. How can we do that? How can we design such a sensor? So, if you see this particular image, this is a schematic. We have drawn this schematic with the help of SolidWorks, In the center of this chip here, in the center of this chip, there are two sensors, one strain gauge and second electrodes, Alright. Now, when you talk about strain gauge, so if you see this particular image, right, what do we see? There are 1, 2, 3, 4, 5, 6, 7, 8, 8 strain gauges, The reason of using so many strain gauges is to cover the entire area of tissue and to see multiple points in the tissue, and to understand multiple points within a tissue. That is why we have 8 sensors, 8 strain gauges. Alright. If I magnify it further, then I can see a single strain gauge which is shown here in the B section of our image. Alright. And the material that we have used to fabricate the strain gauge is P dot PSS. This is a conducting polymer. Okay. Now, what we have done? Let us see what we have done. You see this. Okay. This is the silicon wafer. Now, we have grown oxide on silicon wafer. So, I will just write 1, 2, 3, 4. So, it is easier. Alright. 1, we have silicon wafer. Second, we have oxidized silicon wafer, that means we have grown oxide. Third, we have created contact pads for strain gauge. Fourth, we have fabricated strain gauge. Fifth, we have deposited insulating film on strain gauge. Sixth, we have now deposited N pattern gold electrodes. 7, we have SU8 pillars on gold electrodes. 8, we have made SU8 pillars conducting, and 9th, we have released the sensor. Right. Once again, let us see slowly. First step is take a silicon wafer. Second step, grow silicon dioxide on silicon. Right. What is third step? Third step is we have now deposited electrodes, right, using chrome gold on silicon dioxide which is on insulator, which is an insulator, and this silicon dioxide is grown on silicon wafer. Fourth step, what is the fourth step? Now we have deposited SiO2 on chrome gold on SiO2 on silicon. And how we do that? You know it, right. So, see, for patterning this we are using a photolithography technique. That means that we will deposit chrome gold, right, and then we will pattern chrome and gold with the help of photolithography. All right. Now, in this case, on this pattern electrodes we have deposited, am I correct? No. So, you see, in this particular case we have P dot PSS for strain gauge. So, let us see once again silicon dioxide on silicon, then third step is chrome gold electrodes on silicon dioxide which is on silicon. Fourth step is P dot PSS, that is patterned again using help of photolithography on chrome gold on silicon dioxide on silicon. So, the bottom layer is silicon, next layer would be silicon dioxide, next layer will be chrome gold electrodes, on that layer we have P dot PSS strain gauges which you can see on A and B of the SEM image. Next step, fifth step, process number 5. Now we have silicon dioxide on P dot PSS on chrome gold on silicon dioxide on silicon. Okay. Next step, which is sixth step would be, now we have gold electrodes. So, we say chrome gold on silicon dioxide on P dot PSS on chrome gold on silicon dioxide on silicon, right. Sixth step will be SU8 pillars, on chrome gold on silicon dioxide over P dot PSS, that is your strain gauge, over chrome gold over silicon dioxide over silicon. Last step, right? No, eighth step would be, we make this SU8 conducting. We make SU8 conducting. So, SU8 conducting, and then entire this process is there. So, SU8 on chrome gold on silicon dioxide on P dot PSS on chrome gold on silicon dioxide on silicon, right. And final, the ninth step would be, you take out the, detach the sensor or the biochip from the substrate. How you can detach biochip from the substrate? Can you do that? You cannot do that, right. So, when you grow silicon dioxide on silicon, on that you can use PDMS. So, if you see the screen, this silicon dioxide we said here, right, silicon, then silicon dioxide, right. Second step would be, this step would be silicon dioxide, right. On this silicon dioxide, if I have PDMS, then I can detach it at ninth step. If I do not have PDMS, then I cannot detach my sensor or cannot detach my chip from the substrate, Why we have to detach the chip from the substrate? Because this is a flexible MEMS. And when you talk about flexibility, we have to use PDMS or any other flexible substrate, right. So, this silicon or the oxidized silicon will help to form the base of the chip, alright. So, in this case if I want to detach the chip from the substrate, then I have to use PDMS or a flexible material, and on that I had to do or I had to perform this entire process flow, alright. But if I do not want to detach it, if I want to use a solid sensor, if I do not want flexible MEMS, then I can directly use oxidized silicon wafer. Okay. So, let us see once again, so that we are sure, right, that both of us, you guys and me, we are on the same page. So, what we do? We start with an silicon, or we can say oxidized silicon, oxidized silicon. If I want to have flexible MEMS, then this layer can be PDMS, alright, can be PDMS or silicon, is a SILICONE, flexible, it is a polymer, PDMS or silicon on the oxidized silicon. This can be PDMS on oxidized silicon. Then next step is your designing a contact pad for strain gauge. Next step would be to fabricate strain gauge. Next step would be to deposit an insulating material on strain gauge. Next step would be to create a gold pad. You see here gold pads, this is single, these are multiple gold pads, right, 8 in number, because we have 8 sensors, 8 strain gauges. Now, we have 8 gold pads. Okay. How you can fabricate this gold pad? Using photolithography. On this gold pad, we have now SU8 pillars. You can see here SU8 pillars, this is the next step. Now, SU8 is non-conductive polymer. So, we can make it conductive by depositing or by coating SU8 pillars with a metal. Which metal? We can use again chrome gold, right. So, here we have coated SU8 pillar with a metal, and finally, we are able to detach the chip or the sensor or the MEMS device from the base which is our SiO2, right, over silicon. We can detach PDMS with sensors completely, and this would be our flexible sensor. This will be our flexible sensor. If we do not use PDMS in this particular stage and we continue to fabricate the device, then at the end of this we will end up somewhere here. We will not be able to detach the device. That is fine, for some application this kind of devices also will also work. Okay. Now, if you see on the right side, what do you see? This is the detached device and it is flexible. This is a detached device and it is flexible. So, how many contact pads would be there? You see, for a strain gauge we require 2 pads, you can see 1 and 2, right, 2 pads for strain gauge. And how many pads for electrodes? 1, just 1 for the electrode, right. So, we consider electrode is the gold pad over which there is an SU8 pillars, gold pad. So, gold pads on which there are SU8 pillars, or if we talk about one single, then gold pad with a SU8 pillar, and that SU8 pillar is conductive because we are coated with a metal. Okay. Now, we have a sensor. So, let us see how we can use this sensor further, how we can use this sensor for our application, that is our application is to delineate or to understand the electromechanical phenotyping of breast cancer. We have to understand whether the tissue is cancerous or not. So, if you see here, like I said, for each strain gauge, how many pads we require? We require 2 contact pads, 1 and 2, and then on that there is an insulator on which there is an electrode on, and that electrode consists of a SU8 pillar. So, this is a top view, it looks like this, right. Somewhere your electrodes is like this, right. I am not just making it solid so that we can understand. So, now how many contact pads for here? 1, right. How many? So, we can name it as 3. So, how many contact for here? 1 and 2. So, total is per chip per sensor. So, if I go back, if you see here, right, this one, there are 3 electrodes, because one for the there are 3 contacts, one for the electrode and 2 for the piezoresistive sensor. So, that is why you see here 1, 2 and 3, 2 for the strain gauge and 1 for the electrode. One more thing, if you have observed, is here we have a zigzag pattern or a ribbon pattern for the contact. Why we have not made a straight contact? Why we have not used this kind of pattern for contact? Why we have used ribbon pattern? The reason is that we want to reduce the stress. Because this sensor would be flexible, in nature. So, we have to bend the sensor. Now, if you see this one, so the sensors are right in the center, right, they are extremely small, and if I go on magnifying it, I can see here clearly this one for gold pad, for the gold electrodes, and this one is for piezoresistive sensor, correct. Now, this is another diagram, you can see here very clearly what I mean. So, we have strain gauge and when we have electrodes, 8 strain gauges and 8 electrodes, right. You see 1, 2, 3, 4, 5, 6, 7 and 8. You have 8 strain gauges and 8 electrodes. So, 8 piezoresistive sensors, 8 electrodes. Okay. And there are certain biomarkers that are there through which we can confirm whether there is cancer or not. Some of those are prostrogen biomarkers, estrogen biomarkers, Ki67, then we have H&E images. So, these are all images of the tissue, okay, using different biomarkers, and from this the path lab will tell us whether there is a cancer or not. Okay. Now, there are certain biomarkers, there are certain cancers within the breast cancer, there are approximately 12% of breast cancer within breast cancer, okay, that are called triple negative breast cancer. Within the bigger umbrella of a breast cancer, there are around 12% of breast cancer which are known as triple negative breast cancers. Why? Because none of the biomarkers are present in the breast cancer tissue, none of the biomarker. Which are biomarkers? Estrogen biomarkers, prostrogen biomarkers, HER biomarker, right, none of the biomarkers are present. So, it is very difficult to identify such tissues, and that is why the device that we are fabricating or we are understanding comes into play, which is very important or plays an extremely important part in identifying those tissues which cannot be identified with the existing biomarkers. And that is not a claim, this we have just done study using some patients or few patients, and we have to make sure that we have enough number of patients to claim that this particular device can play an extremely important role to identify triple negative breast cancer. So, how now we are identifying or delineating the normal tissues from the cancerous tissue? Okay. So, for that we have to load the load the sensor on the 3D printed cone. Why? So that we can indent the tissue, we can indent the tissue. So, let us see on the screen what we have. We have a 3D printed cone right over here, and we have attached the flexible sensor right onto the 3D printed cone. At the bottom which you can see here, right, there is an electrode or a microgrid for holding tissue, and this is the image where we can see a breast tissue core on microgrid. Right. Now, what will happen if I indent this tissue, if I press this tissue, then the piezoresistive sensors on my MEMS device would bend, and that bending will be corresponding to the elasticity of the tissue, correct. You know, right, that this sensor, this chip has piezoresistive sensors and it has an electrodes 8 right. So, when this sensor touches the tissue which is placed on the microgrid, what will happen? Because of the stiffness of tissue, the piezoresistive sensor will bend, and this bending will cause change in resistance, and that resistance corresponds to the elasticity of the tissue. Second part, there are about 8 electrodes on the sensor, or there are 8 electrodes on the MEMS device. When I apply a voltage between the microgrid, that is here, right, apply voltage between microgrid and the electrodes and these electrodes, and the tissue is in between, right, tissue is in between, apply voltage between these 8 electrodes and a microgrid. What will happen? There will be change in the resistance of the, there will be change in resistance, or we can see the different resistance depending on the resistance of the tissue. How you can see the resistance? It is very difficult to measure the resistance or see the resistance, right, change in resistance. But what we can do is, when we apply voltage, we can measure current, right. This change in current will correspond to the change in the resistance of the tissue. Thus, we are not only able to measure the elasticity of the tissue with the help of piezoresistive sensors, but we are also able to measure the resistance of the tissue with the help of applying voltage across the tissue with the help of electrodes and the microgrid. So, how this thing works? Right. So, you can quickly see this is a video that 3D animation that I have created with the help of Maya, and this is a stage. Now, we have placed the bottom microgrid array, this 3D printed cone, and on this cone we will be loading our MEMS device. The MEMS device consists of piezoresistive sensors and electrodes. When we attach the MEMS device onto 3D printed cone, we have to load the 3D printed cone onto the micro manipulator, We loaded the cone. Now, we will place the microgrid on the stage. On that we will place the tissue. and then we will press the tissue, as you can see clearly, right. We are pressing the tissue and we are measuring the electrical and mechanical property of tissue, right. So, same thing goes here, same thing goes here. This is where we are placing the tissue, you can clearly see, right. We are placing the tissue onto microgrid. We have just seen the schematic of the sensor, and now the sensor or the MEMS based device that is detached from the substrate is now stretched to evaluate the performance, that we get the same base value of the piezoresistor and to see whether it will break or not. We have also tested bending, by bending the MEMS device we have tested its property. Now, when you load the device and you can see with the help of micro manipulator we are indenting the tissue, right, it goes down, it touches the tissue, indents it, gets the data, comes back. Correct. So, with the help of this what we can understand, that we can measure the electrical and mechanical property of tissue. Now, you can see here this is a SEM image and is about 5 millimeter. So, total chip dimension is close to 10 millimeter, right, almost double of this, little bit more than that. So, I think it is close to 15 millimeter, the overall chip is 15 millimeter, but you see where are the sensors? Sensors are right over here, right over here. Within an area of 1 millimeter we can have two sensors, one is piezoresistor sensor, another one is the electrode, right. So, this is the SEM image, you can see here there are two lines, right, that goes out of the piezoresistor sensor. From here you can see one and then another one from here, right, and the center one is for the contact pads. This one is for the electrodes contact pad, this one and this one will be for piezoresistive sensor, piezoresistive sensor. Because there are 8 sensors, we have about 24 pads, we have about 24 pads. You can see 3, 6, 9, 12, 15, 18, 21, 24, right. About 24 contact pads we have to fabricate, or we can pattern using chrome gold to take out the contacts from piezoresistor and electrodes. And how many piezoresistor and electrodes are here? 8 piezoresistors and 8 electrodes. Okay. You can see here now we have strain gauge, array of the strain gauge, this top view, cross sectional view of strain gauge, this is SEM image, and you can clearly see a single strain gauge, right, SEM image of a single strain gauge. Now, these are gold pads, you can see gold pads on insulator on strain gauge. So, that what does it mean? We have a substrate, we have oxidized silicon wafer, let us oxidize, so SiO2, right, SiO2, we have silicon, and this one is our PDMS, right. On PDMS we have this strain gauge, right. So, let me just draw one strain gauge, so it is easier for us to understand. Let us say this is a strain gauge, right. On this strain gauge we have insulating material, which is our SiO2, this is our strain gauge, on this strain gauge I will have the chrome gold pad, which you can see here, correct. Single pad, you can very clearly see in this image there is a strain gauge, and then there is a insulator over which there is a gold pad. What is the size? So, 20 micron is this size, 20 micron. The bar line shows 20 micron. So, it is about 50 microns, it is about 50 micrometer diameter. Okay. Clearly see the SEM image of a gold pad on insulator on strain gauge. So, where are SUR pillars? Let us see where are SUR pillars. SUR pillars, you can see this image, and in this image what we see, there are SUR pillars, right. You can see this SUR pillars, and in the next image you see that the SUR pillars are like they are not stuck well onto the PDMS, but they have fallen down, right, because of the poor adhesion. Right, poor adhesion. And why there is a poor adhesion? Why there is poor adhesion? Because of the moisture content. One of the possibilities, because of the moisture content on the layer, on the PDMS layer, these SUR pillars have fallen down. You can see SUR pillars, this is a top view, cross sectional view or side view, here, see SUR pillars. This is grid, micro grid, right, and you can see a fine mesh here. Again this is because of the skipping the process or not following the recipe correctly. We can see the micro grid detaching from the pad, right. This is a failure, but it should be like this, not like this. Okay. On this micro grid we place the tissue. These are few of the results, that I have used for this particular module, and here what we have to see is how the elasticity changes from normal tissue to ductal carcinoma in situ to invasive ductal carcinoma. Normal tissue, ductal carcinoma in situ, invasive ductal carcinoma. These are the stages of cancer can be identified. Okay. While as we know, if the cancer occurs in lobes, it is a lobular cancer. So, from normal tissue to lobular carcinoma in situ to invasive lobular carcinoma. Okay. How the elasticity changes and how the resistance changes. So, we can see here now within that normal tissue or within DCIS or within LCIS, we are also measuring the epithelial and stromal lesion. First let us just see epithelial lesion. Epithelial lesion is given by blue color. You can see that normal tissue are somewhere around 40 kilopascal, while the cancerous tissues are around 10 kilopascal. Now, if you see in terms of elasticity, how come the elasticity of a cancerous tissue is less compared to normal tissue? Because we have now cut the tissue which is from biopsy into slices, thin slices. This slice thickness is close to 10 micrometer. So, what we think is when you decrease the size, the elasticity does not follow the same thing, is not similar to when you have a whole tissue, because when it is a bigger tissue, larger tissue, then we can see that the elasticity of the tissue which is larger, the cancerous region is more stiffer compared to normal. But when we talk about the tissues which are thinner, the slice is thin around 10 microns, then the elasticity which is from the normal tissue is close to 40 kilopascal, while the elasticity from the cancerous tissue is about 10 kilopascal. This is when we are talking about epithelial region, right. And if you see DCIS, let us say DCIS, the DCIS somewhere is in between the invasive ductal carcinoma and normal tissue. What about resistance? Let us say the resistance is close to 340, 335 to be like a little bit precise average value, while if you see the resistance of the invasive ductal carcinoma is close to 700, while the resistance of ductal carcinoma in situ is somewhere in between, right. This one and this one. Second, if you see the red color is stromal region, stromal region in the case of normal tissues its elasticity is around 100 kilopascal, or if we take average about 90 kilopascal. In the case of invasive ductal carcinoma, it is somewhere around 25 kilopascal, while for the ductal carcinoma in situ it is somewhere around 38 kilopascal, about 40 kilopascal, right. So, what does that mean? My point is that our sensor, the sensor that we have designed, the sensor that we have seen right now is capable of delineating normal tissues, ductal carcinoma in situ and invasive ductal carcinoma. That means, it can measure the change in the tissue property, elasticity and resistance as the disease progresses or as a disease progressed. And this was case of ductal carcinoma in situ. But if you take the case of lobular carcinoma in situ, so if you see from normal tissue to lobular carcinoma in situ to invasive lobular carcinoma, we can again find a distinguished clear cut pattern, We can easily delineate a tissue which is normal, a tissue from lobular carcinoma in situ and a tissue from invasive lobular carcinoma. And thus, our sensor is able to measure the change in the elasticity as well as resistance as the cancer progresses from normal to invasive, right guys. So, what we have learned? We have learned the flexible MEMS, right, which is capable of delineating the normal and ductal carcinoma in situ or lobular carcinoma in situ and invasive ductal carcinoma or invasive lobular carcinoma, right, tissues from that is obtained from the biopsy, right. And this is the setup, the experimental setup, right. This is micromanipulator which is right over here, micromanipulator MP285, right here where we have loaded the tissue and you can see the magnified version here, right, and we have some electronic module, we have an inverted microscope. This is a stage inverted microscope we borrowed from the AFM unit, atomic force microscopy, right, and with the help of the experimental setup we were able to measure the changes in the tissue. Okay. So, I hope that you guys understood what we mean by the designing flexible MEMS for applying in this particular area where you want to understand or delineate between normal and cancerous tissues. Right. In the last class what we have seen, a piezoresistive cantilever that can measure the change in the mechanical properties of tissue. In this class what we have seen a sensor or a MEMS based device with multiple sensors that can delineate the tissue properties or tissue cancerous tissue and normal tissue along with a ductal carcinoma in situ or lobular carcinoma in situ with the help of electrical and mechanical signatures. And mechanical signature is nothing but elasticity and electrical signature is nothing but resistance. All right. In the next class let us see how we can design a complex sensor which can do electrical, mechanical and thermal properties of tissue together. Till then you go to the lecture, I will see you in the next class.